In our last lecture, we have talked about how to implement the Gauss-Seidel method for the problem that we are discussing, the nuclear fuel rod heat conduction problem. And then at the end, I have showed you the result. I have already implemented the method. And I'll show you in this lecture how to start working on it. Whenever we do numerical simulation, as we'll talk later on, that we are never sure about our simulator. So we start from an easy problem. We look into this problem very carefully. We make sure that whatever we have done for the easy problem is right. Then we add layers of complexities over it, one complexity at a time. So what I'll do in this lecture, that I'll get you started with the Poisson solver that is needed, and then you can modify the solver to suit the exercise problem. So my suggestion in this lecture that you get ready with a pen and paper so that you can take notes from this lecture, and you will also write the program with me in this lecture. So some of the equations we will be using in program, you will miss that. So you will take note and write everything, all the equations, boundary conditions, topping criteria in your paper. So with this video, whenever you need, you will pause it and you will keep on writing the program with me. That is the way you will learn how to do it. And then, of course, this will be for an easier solution, but then you will know how to do it for the more complex problem. So let us recall we are solving this problem. We are in word domain really. So this is the problem domain, and here two sides Neumann, two sides convective type condition we have. Solving this Poisson equation, this is del 2 theta equals -1. Now when you implement this problem, you will have major difficulty in implementing the boundary condition. So that is why we will just simplify this and implement the equation first, and that is what I am going to show you, and then you will be working on your own to implement the boundary condition, one boundary condition at a time. That's the idea. So what we are going to do here is that we will implement this problem, exactly the same equation, but the boundary condition will be theta equals 0 at all boundaries. So this is, you may think that, well, this is a hypothetical condition, but this is not an hypothetical condition. This is a high BO number limit. So for instance, you have seen that the kind of boundary condition, if we have convective boundaries all over, then the kind of boundary condition I am getting del theta del x or del theta del y plus bi theta equals 0. And when BO number is high, then you can write this as 1 by BO number del theta del x plus theta equals 0. This is the condition. When BO number is high, this term actually goes down and theta becomes 0. It says that a lot of heat transfer from the boundary. So boundary temperature is pretty much equal to the outside temperature because of high heat transfer coefficient. So this is a condition. This is not hypothetical. This happens all the time in real application actually, but it is easier to implement. Once you implement this, also later on you should be able to check your result of the actual exercise condition by changing simply the BO number and see that what is happening there. All right, so before we proceed, I want you to note few things down in a pen and paper. I'll not write it once again. I'll now go back to the code window. So the discretized governing equations, you please write it in a pen and paper. And these are the discretized boundary condition in all boundaries. So that is trivial, but this discretized governing equation, you write it in a piece of paper. And specifically, you write the expression of this as ai j minus 1 j plus 1 is 1 by delta y square, and ai minus 1j, ai plus 1j, y by delta x square, and aij is minus 2 delta x square minus 2 delta y square. So please write this equation and write this aij's in a piece of paper before we proceed. course, here we do not have an initial condition. This is not a time dependent problem, so we cannot have an initial condition. What we have instead is an initial guess, and for our solution we'll take this initial guess to be 0. So now I'm about to start writing the program. Here I'm in a spider window, and this part of the program that is plotting, this plotting part I have already copied from a previous work that we did in this course, because I don't remember all this detail really all the time. That is why I just kept it there, copied it from there. So we'll use this part to have the contour plot. And herein we will need NumPy, we'll need matplotlib for the plotting anyway. So here in the main program, we will now write the program. Okay, so let's start from here. First, we have to give certain value of nx and ny, and because we really don't need a very high resolution here, so I'm starting with this nx and ny both to be 51, and then the length that we'll take in both direction, we'll take it to be 1 in x direction length, y direction length. Okay, so now we'll decide this, our error epsilon, where we'll put the stopping criteria. That would be our 10 raised to minus 6. This is our stopping criteria, and this over relaxation factor. So let us say UR as under relaxation. This is the kind of solver where you will need really under relaxation. We'll use under relaxation or not, let us just keep it as 1 for now, and we can play around with it later, but you always start with 1. Then this iteration loop, when the program will run, we have to set a maximum number of iterations. So you put a big number there. Let us say this is like 10 lakhs. So it's quite a big number. So now the numbers are given. We are starting for the real thing. Our unknown u is np dot zeros. That would be nx, ny. This will be our array that spans through the entire domain nx, ny. It is defined over all points. And now I have to define this aij, plus 1j, etc., etc. So the way how I'll define that, I'll come to that. And let's first start with this for I equals, for I in range 1 to nx minus 1, because the last two will come from the boundary condition. These are the interior points we are talking about. And for j in range 1 ny minus 1, this covers the interior points. The boundary you will take a look later. And of course over this there will be this iteration loop. So let's put this iteration loop for k in range max 8 within the iteration loop. Now I have to calculate that r value, that is rij, but we will overwrite, so this is not an array. So let us say we name this residual r, which will be equal to source term. So we need a source term here. Source term, our source term is -1. That is the source term in our equation. That will in the right hand side anyway. Source term minus a star, this ui plus 1, j ui minus 1j, they are both same. Their coefficient is 1 by delta x square. So we can keep them together. So ui minus 1 j plus ui plus 1 j. So that goes 2 terms. Then next term is minus b, is basically very similar. It would be I, j minus 1 and j plus 1. So I can put it like this. This is I, j minus 1, j plus 1. here I have this coefficient b, and then I have this coefficient c for this uij. So uij. So now let us set this ABC first. So my source term I have put it there, and my ABC is A will be 1 by delta x square, B will be 1 by delta y square, etc. So we need to know this delta x, delta y. So dx is Lx divided by nx minus 1, and dy is Ly divided by ny minus 1. So my A then will be 1 by delta x square, and therefore this is 1 divided by this dx star dx. Similarly, my b is 1 by delta y square, and c will be 2 by delta x square, 2 by delta y square. So we can simply take it as 2 times a plus b. That should be it. So ABC is done, reiteration is done, source term is done. So here now this, how we will update this. This is the residual, and my uij is equal to last value of uij. So I am not storing two iteration values, I am simply overwriting it, plus this residual divided by this aii, and all aii's are c actually. So residual by this c, and then under relaxation factor, although we have taken it 1, we can change it later. So this is my under relaxation factor. This gives my new u, and now of course I have to stop iteration at some point. So for that I have to calculate the square of these residuals. So let's start with this RMS 0, and now this RMS equal to RMS plus residual square actually. And then what we can do, we can take a square root and divide by this n actually. So that will give us a better idea. So here let us say this actually completes the loop. So RMS is equal to np dot squared of RMS, and you can divide it by the total number. Even if you don't divide, it will work. So it should be nx minus 1, ny minus 1, but it will not make much of a difference here. The effect of that minus 1 will be small, and so this calculates the RMS, and then we have to break the loop. If RMS is less than this epsilon value that we have set, then it will break the loop. Okay, so this is pretty much what it is. What we are missing here is the boundary condition and initial guess. Okay, so we need an initial guess, and initial guess will be all over 0. So u at equals 0. Okay, so this gives my initial guess. Now boundary condition. So boundary condition is 0. At the boundary the theta is 0, and anyway we have used this u equals 0 because of np dot 0. So anyway at the boundary theta is 0. So we are not doing anything at the boundary conditions boundary. So this is my initial guess and not initial condition. BC is set u equals 0 anyway, so we don't bother about it. We can track our solution. So for instance, we can print here number of iterations and this RMS. Of course, there are many things we can do to improve this code, but the important thing is to check it. So here this will simply give you number of iteration and what is the RMS value. It should come down slowly. If I run this, it will take few minutes probably, and then it will give the result. This is usually slow in Python. Python itself is a slow language, but this is for our practice, so we should be all right. If you want to make it faster, you have to use either a different language such as Fortran or C type language, or in Python environment, you have to use SciPy sparse solver like that. Then using SciPy, because SciPy is inherently C, so you will have a speed up, but here it might take, depending upon all these values, it might take a moment. So let us see if we run it, what happens. I'll probably make it faster here and I'll show you. So to run it, well, so it looks like I made a mistake here, and it should be -2, which I made +2. And we are now ready to run the case. Everything else should be all right. So let us see, let us run the case. You can see that the case is, we have run the case, and here you can see this with iteration 2620 iteration, it has converged, and this is the result. It's pretty symmetric. It makes sense to take 1/4 of this case. At the center, the temperature is high. Outside, it is going 0 because we have set 0. So it looks good. We can now play around with this code. So for instance, I make this source 0, and then it's a trivial solution. Now everything 0, so no source, temperature 0 outside, and initial guess is 0. So it will give only 0 solution, but we change one boundary. Let us say my y equal to 0 boundary. I'll put there as my 1. So y equal to 0 means this 0 to nx, that will be 1. So I have, this is my 0th and it is my 1. So I have set the boundary condition. This is my boundary condition. If I now run this case, my case is running here. You can see the converse solution. Y equal to 0, this is 1. And then as I go up, it becomes 0. So it looks quite all right. If I make x equals 0, y equals 0, both 1, then I can set another boundary condition that this is 0 and this is equal to 1. Let's try it. The case is running now. It is possible to have analytical solution like this. All 0, 1, boundary 1, or 2 boundaries 0, 2 boundaries 1. It is possible to have analytical solution like this. So whenever we solve such problem, after getting such solution, we first try to match with the analytical solution, and then we go for more complex problem for which we do not have analytical solution. Here we do have analytical solution. You can also see that we can actually cut from here along this diagonal, because along the diagonal it is symmetric, and we can solve only within this triangle. Implementation will be a bit tricky there, so we are not doing that, but once you implement, you can cut down your computational time there. So in this way, you can make your problem more and more complicated. You start with the simple problem. Once again, you start with the initial problem that we were talking about. You have a source, and then you have all boundaries are 0. So that was our initial case. So this was our initial case. And then you can make it complicated. You can have a source and 2 boundaries 1. That would be another case. Both this boundary 1 with source. How does it look like? I don't know. Let us run. So you see that it is actually similar to no source. This is source, no source. This is what we have is source. So they look very similar, source or no source. So in 2 boundaries are 1. So this is the way you can play around with this and try to get more out of this code. But your goal here is, if you are coding with me, then your goal here to change this code so that you can solve the exercise problem. And I'll not show you the exercise problem solution here in the lecture, but later on I may give you the code so that you can take a look. But you have to do your solution and see that you are getting correct result. You have to convince yourself that your result is correct. How you will convince yourself that your result is correct? That is something we'll talk about it later. So now we have implemented a simpler problem in Python. And for your exercise, the goal is you change one boundary condition at a time. This one is the keyword here. Don't do too much changes. And eventually you will reach the solution of the exercise problem. Not in one shot. One boundary at a time you change. With zero source, all but one homogeneous boundary condition and theta equals 1 at the non-homogeneous boundary condition, you should be able to match the analytical and numerical solutions. Analytical solution you can do using separation of variable. If you don't know how to do it, then you will find the solution. This is a standard problem. The standard solution you will find from heat conduction book or engineering mathematics books. So you use that solution and make sure that you are getting the correct solution, analytical, numerical. Earlier we have talked about how to match the analytical and numerical solution. It is best to match them using line plot and not just contour, because from contour you will get only qualitative match. For quantitative match you have to go through line plot, as I have already shown in our discussion of one-dimensional transient heat conduction. So that's all for this lecture. Thank you, and I'll see you in next class.